Question 5. The percentage biomass of iron in steel wire is determined by a student. The student takes 680 milligrams or 0.68 grams of the wire with an excess of sulfuric acid so that all the iron in the wire forms Fe2+. Makes up the volume of Fe2+ to 100 centimetre cubed, takes 25 centimetre cubed portions, titrates each portion with 0.02 mole per decimetre cubed potassium manganate 7 solution. Give the equation for the reaction between iron and sulfuric acid. Well, iron's Fe, sulfuric acid is H2SO4. A metal and an acid always give hydrogen gas, and we know that it makes Fe2+, sulfate ions are SO4 2-, so it's going to be FeSO4. Calculate the mean titer from these titration results. Titer is a volume, so let's have a look at the volumes that we've got. Titration number 1 gave 22.90, 22.70 from titration number 2, and titration number 3 22.60. For concordant results, i.e. those are results that are close enough for us to use, they must be no more than 0.1 apart. Well, 1 and 2 are 0.2 apart, so they're no good. 2 and 3 are 0.1 apart, so we're going to ignore titration number 1 and just take an average, a mean, another word for an average, of titrations 2 and 3. 22.70 added 22.60 divided by 2, because there's only 2 titrations that we're actually using, gives 22.65 centimetre cubed. Give the overall ionic equation for the oxidation of Fe2+ by manganate 7 ions in acidic conditions. So what you actually do here is Fe2, you've got to write half equations, then balance them to get the overall ionic equation. Fe2+ goes to Fe3+, so the Fe2+ is going to be oxidized by the manganate 7 ions, that's an oxidizing agent, to Fe3+, and for a half equation I've got to add electrons to one side or the other to balance up the charges. 2+ on the left, 3+ on the right, electrons and minuses, so I'll add an electron on the right hand side. MnO4- goes to form Mn2+, manganese 2 ions. But the problem is, what do I do with the 4 O's? A little trick that I can always do is I can always add H+, and I can always add waters. I can always add those at any time that I want. So where can the 4 O's go to? Well, I'm only allowed to add H+ and waters, so let's add some waters. That gives a place for the O's to go to. I'm going to put 4 in front of it to balance up the 4 O's. That creates 8 H's, so the 8 H+ then must be on the left hand side. So remember, I'm always allowed to add H+ in waters if I need to balance a half equation. Let's add up the number of plus and minuses on the left hand side and decide how many electrons I need. And I'm going to need 5 electrons on the left. Let's check. 1 minus 7, 8+, that gives 7+ overall. On the right hand side there's 2+, so I'm going to need 5 minuses on this side, so a minus and 8 plus is a 7+. 5 minuses give 2+ to balance with the 2+ on the right hand side. Now I add everything on the left and everything on the right, and then I cancel anything left and right. But before I do that, I've got to get the electrons to be able to cancel. So I've got to get the same number of electrons in both of these half equations. So I'm going to multiply this one by 5 Fe2+, 5 Fe3+, of 5 electrons. The other one stays the same, so that when I add everything on the left, 5 Fe2+, MnO4- 8H+ of 5 electrons, and then everything on the right, Fe2+ plus 5 electrons, 4 H2O Mn2+, there's the same number of electrons on each side. They cancel, and it ends up with this equation here. State the colour change seen at the end point of the titration. Well, what's actually happening is Mn2+ are colourless, or very, very, very pale pink. They're pretty much colourless. But as soon as I add a drop of manganate 7 solution, which is purple, it will make the solution purple. So that's how I know that the end point has happened and that all of the Fe2+ has been oxidized to Fe3+. But one more drop of Mn2+ creates a colour. Now it's going to be very, very pale purple. You don't want to run an awful lot more through, just one more drop and then stop it, otherwise your titrations are going to be wrong. So just maybe one drop excess after the end point when all the Fe2+ has been oxidized to Fe3+. So it's going to be a very, very, very pale purple. Name the piece of apparatus used for the stage of this method. To take 25 cm3 portions, I'd use a pipette. Add in potassium permanganate solution, you use a burette. The balance to weigh the 680 milligrams of iron has an uncertainty of plus or minus 0.005. A container was weighed and its mass was subtracted from the total mass of the container of the wire. So you've got the container weighed first of all, you know the mass of the container, and then you've got the mass of the container with the wire in it, and you subtract the two to get the wire. You've got two results there, two readings. So what you do is you take the percentage uncertainty and multiply it by the number of readings. That's times 2 is 0.01. So because I've got two readings, the uncertainty is doubled, and then the percentage error is the uncertainty divided by the mass of the iron that I use. So now then, this is in grams, so I'm saying that it's 0.005 times 2 grams is the uncertainty, so this got to be in grams. The small unit value, like milligrams up into grams, divided by 1,000, 0.68, and I multiply by 100% to get a percentage, 1.47%. Everything here is three significant figures, 680 milligrams, so let's have that as three significant figures to 1.47%.